So last time I made a statement or an argument that the internal energy is a state function. Okay, so what I wanted to do is this really simple, like almost like a thought experiment. So what would be the consequence of internal energy not being a state function? So considering this sort of makes you realize how absurd it is for it to think that it might not be a state function. In other words, to think it might depend on a path. So here, I don't know if you've, I think you should just look at this, read it. Jack, don't take the opportunity to fall asleep. So take a look at it, read it, and then I'll talk about it, okay? And come to some. Oh, do you have? I emailed these to you, so you could look at it on your device, or you could look at it on here. But I think if I put the whole thing on here, it might be too small to read. I'll do it anyway. There, the whole thing is, and you could see it on there. I can't see it that well, but you can. And I just want to say that these are not trick questions, all right? They are as easy as they look.
Dr. Cooley.
Yeah.
So where it says what is U1 for the Aurora process, like that question?
Yeah.
Would that be? Would that
That's
just
the
be?
sum of the other. That's this.
Oh, yeah.
Right.
Yeah. So would it be X minus Y pretty much?
Yes, that's exactly what it would be. All right, I think we're ready to talk about this then. Let's see. Okay. So, you know, you have two states. You take a path A and you go from state 1 to state 2. And it says, let's say that U increases by an amount X. Okay, now we're at state 2. U has increased by an amount X. And now it says, so this is X. Delta U along path A, going from state 1 to 2 would be X. And now what it's telling you is if it was path dependent U, and you went along a different path, path B, it would increase by an amount Y, where let's say for the sake of argument, Y is greater than X. So that would mean that if you went in the opposite direction from 2 to 1, that it would be minus Y. So this would be minus Y. And so if you thought about the whole process, the cycle of starting at 1, going to 2, and back to 1, you would add, you would say that's X and minus Y. You would say it's X minus Y. And you've already said, let's see, that Y is less than X. So this is a positive number. All right. So if internal energy depended on path, then you could have a cyclic process that got you back to where you started from. So this cyclic process taking from 1 to 2 along path A and then back to 1 along path B, and you would gain a positive amount of internal energy. And that positive amount is X minus Y. So, you know, what would be the consequence of that? So it means you could basically, by cycling back to the same state, you would increase the system's internal energy every time, right? So that's really fantastic. You know, if that were able to be done, okay, then we wouldn't ever have to worry about fossil fuels or nuclear fusion or nuclear fission or anything like that. Okay, we would be able to do work in, you know, we could use that energy to do work and we didn't have to do anything to get it. So it's like if U is not a state function, then, you know, then work would be free. Okay, so that's not the way it is. Okay, so if this were true, then could increase internal energy and use that energy and you could do this continuously. You know, but I've been telling you that the first law, right, is like saying there is no free lunch. You know, if you're going to do work, that work has to come from energy from somewhere. It can't just come from nowhere. So, so the consequence would be we wouldn't ever need to worry about energy. Okay, that we wouldn't need fossil fuels. You know, all of these things. Nuclear fission, you know, anything that produces energy. Okay, energy would just be renewable just by doing this cycle over and over again. All energy would be renewable. So the extra energy could be used to move a car, to heat a room, or operate something we call a perpetual motion machine. So you could use this energy to operate a perpetual, it's spelled today, motion machine. And, you know, there were a lot of people who've tried to make things like this and failed. Okay, so when I talk about alternate statements for the first law, and I gave you a few of these, right? But here's a really a good one. Here it is. U is a state function. And another way of saying that is a net gain of internal energy is not possible. It's impossible for a cyclic process. So these really go hand in hand. Another way of saying this is a perpetual motion machine is impossible. And they've tried, like I said, many people have tried and failed. Because, you know, you can't produce work without some other form of energy getting used up in the process. Or as I have said, you know, you get what you pay for. There is no free lunch. Okay, you can't win. That's another really famous one. And I like that one because then the second law becomes you can't even break even. And then the third one is you can't get out of the game, but that's a little hard to explain. And it's kind of not really, it doesn't really work as well as the other two. We'll get to that later. Okay, so we have segued temporarily, very temporarily into chapter 3. And like I said, there's only a couple of sections that we're going to cover in chapter 3. But I do need to cover this because we use the differential du. We use it all the time in this class. We use differentials of all sorts of things. But in particular, we use this, and a lot of other ones. So in this chapter, in section 3.2, it tells you that since the internal energy is a state function, we refer to its differential du as exact. I don't know, is this something you've ever seen in math class? Probably not, but maybe in physics, but maybe not there either. Or maybe in those extra courses where they do the calculus stuff. I don't know. But anyway, whatever you're going to need, you're going to learn here. So what does it mean for a differential to be exact? Okay, what it means is that if you integrate that differential between two states, okay, so what is the integral of du? Well, it's u, well, within a constant, but we're going to do the definite integral between two states. The integral of du is always the same and is always the value of the internal energy at 2 minus the value at the first state. So whenever you integrate a state function, you always get the same thing. It is not dependent on how you got from state 1 to state 2. It's not dependent on how the system got there. So we say that its differential is exact. The integral always gives the same result, regardless of the path that was taken. Okay, so, you know, we have already seen that this is not true for work. Okay, when we did the isothermal expansion, and we did constant pressure versus reversible. Okay, so we started with dW is minus P external dV, and you know, we took a reversible path. Well, I assigned it. I didn't actually do that calculation with you. But if you took the reversible path, you would have you would say that the external pressure is the same as the gas pressure. Remember, it's the same at every point in the expansion. And we would then just call it P. So the integral of dW becomes the integral of P external dV minus P external dV, I should say, which is minus P dV, which is minus nRT over V dV. This is done, we did this on Monday. And if it's isothermal, we get to take the T out, and all these other things are constants as well. This is minus nRT dV over V from V1 to V2. So this is minus nRT log V2 over V1. That's for the reversible path. Well, I'll share again then, if you don't. Okay, so that's with the reversible path. And if you did the, that special problem, okay, so in class last time, we did the constant pressure. And then at home, you should have done this, and you should have gotten was it 1 mole, I think? 8.314, 305, and then the integral, sure, I should have written this down. Okay, did everybody get this negative 3.52 kilojoules for the reversible path? Did everyone get that, remember? Anybody?
Yes, I got it.
Okay, good, thank you.
Yeah.
All right, so that was, and that was going from, you know, we had the same initial and the same final state. This is example from last class. If we did it at a constant pressure, minus P external dV, just like we did last time. But now this external pressure comes out because it's constant, and we get minus P external times V2 minus V1. And this, remember that this was constant. It was a 2.50 atmospheres. Anyway, we did this in class last time, and we ended up with negative 1.90 kilojoules. Okay, this is done in class. That was the example that you did at the beginning of class, and then you took it and converted it from liter atmospheres into joules. Okay, so this is from the path dependence of work special problem. Okay, this was done, this is constant pressure, and this is for reversible. And it was between the same two states. So work is definitely path dependent. So we cannot do the same thing. These are not the same. Okay. And remember, I also told you, because the temperature is constant, okay, and it's an ideal gas. So what was the change in internal energy? Do you remember in this problem? What was it? For a constant pressure problem.
0.
Yeah, the goose egg here. So this is for constant pressure, constant temperature process, when you had no reactions, no phase changes, you get a delta U equals 0. And since the work is different, the heat is different. So this is the work, but W and Q, well, W plus Q is equal to 0. This is for our particular example. So here the Q is plus 3.52 kilojoules. Here the Q is plus 1.90. And I talked about how you needed heat to flow in, or else the system would cool as it expanded. Okay, so this example shows that W and Q are both path dependent. Okay, and so how do we indicate that their differentials are not exact? Well, first of all, we say that dq and dw are inexact differentials. Okay, so that means their integral between two states is not, is not always the same. Okay, so the integral from state 1 to 2 of dw is not equal to W2 minus W1. I mean, you would never even say the work that a system doesn't contain work. right? Work is the input and the output, or Q is the input and the output. You would never say this. Okay, what we did in each of the examples above to calculate the work was we specified a path, either the reversible path or the constant pressure path, and we got two different answers. So dW is not, when you integrate it, you don't get the same thing. It depends on the path. Okay, I can't say that enough times. So to indicate that work depends on path, and that the integral of dW is not always the same, we put a slash on the dW. We write it as dW with a line through it. Okay, and what this means is it's an inexact differential, and you have to specify a path. That you really can't integrate to get the work until you pick a particular path. Okay, so really the first law in differential form should be du equals dq plus dw with these little slashes like this. All right, so I have to tell you that, you know, I don't always use the slash. It's just the way it is. But I will try at the beginning of this section to use my slashes. So my plans from here on in, and you know, this is really, you know, talked about thermo now a couple of days. Now it's kind of getting more into, like, you know, the nitty-gritty of thermo and pchem. Okay, so I'm going to apply the differential form of the first law to different situations. And your very favorite thermodynamic parameter from general chemistry, enthalpy, is coming up soon. Okay, so let me go on and start with the differential form of the first law and see where it takes us. So the first thing I'm going to do is write it down, du dq plus dw. And now I'm going to tell you that I'm going to consider, or at least say, that there are two types of work, because we are really only going to consider one type of work in this part of the semester, and that is expansion work. That's the only kind that I'm going to be talking about for a while. But I don't want you to think that there isn't some other kind of work, which there is. There's lots of other kinds of work. So what I'm going to do is just specify, is just talk about that there's expansion work. And expansion work is sometimes called PV work. I don't know why, but it is. Well, I guess I do, because it's pressure and a change in volume. So expansion work is the work we've calculated. We did it for the constant pressure expansion, the reversible expansion. But there's another kind of work which inconveniently also begins with an E, and it's called the extra work. And extra work is, we'll talk about later in the semester. And extra work is like the chemical work that a system can do. And how you could think about this is, for example, when you couple, like everyone, if you've studied any biology, you know that ATP is the source of energy for cells, okay? So ATP hydrolysis can be coupled, that first, that provides extra work. It does some work, and it does some work to allow other reactions to happen. So that's one kind of work, is chemical work, where one reaction drives another. And we'll be talking about that late in the semester. There's also like electrical work. If you have an electrochemical cell and it drives current through wires, and that is used to move a small toy or light a light bulb or something like that, that's another example of the kind of work a system can do. So those fall into extra work. And I don't want to talk about them. I just want to tell you that they're there. And now I'm going to make this dW expansion plus dWe for extra. Okay, because I really do have to say that I'm not thinking about extra work right now. So so a lot of times what we do in PChem, we start out with something that's completely general. This actually is the first law in differential form. Okay, it's completely general. And now I'm going to say, okay, no extra work. So I'm going to cross this out and make it du equals dq plus dw expansion. And this becomes, it's gone. Okay, so now it's not as general. And that's what happens all the time in this class. We start with something general and we start to make conditions and specify different things. So now what I'm going to do, because I said we're going to talk about this for different situations. So now I'm going to talk about a constant volume process. Okay? So constant volume process. So let's write our du equals dq plus dw expansion. And of course, dw expansion is minus p external dv, right? That's the definition of expansion work. dw is minus p external dv. See, already I forgot the slash. Okay, so now what happens when it's constant volume? Well, this dv is going to equal 0. If it's constant volume, there's no change in volume. So at the same time, I'm going to change the way I write this dq differential. I'm going to put a subscript here. And what that means is that it's a constant volume process. I've specified constant volume. And guess what? I can get rid of the slash, because specifying constant volume is specifying a path. So I now have du equals dqv, and there's no more slash because I specified a constant volume path. And now I have this great equation. du is dqv, and I'm ready to integrate it. I love integrating equations like this because when you integrate du, you just get delta u. You get u2 minus u1. We're going to call that delta u. Okay, and you don't get delta q. No, it doesn't work that way. We just call it q. When you integrate dqv, you just get qv. All right, so we have delta u is qv. So the change in, and I kind of did this with you a little bit the other day, but this is sort of the more official way. The change in internal energy. I got to this when I was talking about the Bohm calorimeter, but I didn't use the differential form. It wasn't quite proper, but now it's all proper. The change in internal energy is the heat that flows in a constant volume process. So if you measure the heat that's flowing into or out of the system for a process that's at constant volume, you have just measured the change in internal energy. Wow, that's kind of cool. You can measure the change in a in a thermodynamic, very complicated thing just by measuring the heat that flows. So if you measure the heat that flows into or out of the system at constant volume, you've just measured the change in internal energy. Yeah, pretty great. All right. So just going to spend a few minutes. This is kind of also something I told you about already, but I want you to look at it from a little bit of a different point of view. And the thing that I already talked about was what happens when you heat a sample. So what if we just talk about heating a substance? Because remember, I believe I did an example with different heat capacities. Did I? I did that, right? Iron and water. Did I do that in this class? I think I did. No? Well, it doesn't matter. I'll talk about it now. All right. So if you heat a substance, so as you heat a substance, you know, the temperature goes up. Actually, I'm talking about heating a substance that leads to a temperature increase. Oh, go away.
This about like the hydrogen bonds?
Yeah, I did talk about that, except not in this particular case because I'm not talking about heating water.
We talked
Yeah.
about in terms of critical temperature and why water has such a high critical temperature.
I have to look at my notes. Anyway, when you heat a substance, it's just, you know, I was doing the same thing exactly in Gen Chem, so it's hard for me to remember. But so if you're heating a substance and the temperature goes up, so heating a substance resulting in a change in temperature. So you could heat something and not get a change in temperature, right? If you heat water at 100 degrees C and it's liquid, then the heat's going to go into vaporizing that water. So you're not going to actually get a change in temperature. But I'm talking about heating something resulting in a change in temperature. As the substance heats, the temperature goes up. So
Dr. Cooley,
yeah.
did you stop sharing the OneNote screen?
Oh, yeah. It wasn't, okay. Not my intention. Okay, so if you're heating a substance that results in a change in temperature, as the temperature goes up, the internal energy goes up as well. And you could think about that, you know, even if you have like a metal and you have all these metal atoms in a solid, all of these will be vibrating in place. That's all they can do. And so the kinetic energy goes up. They're vibrating faster, right? Or if you have a gas and you heat the gas, okay, all the molecules move faster. The kinetic energy goes up. Well, that's the internal energy. The internal energy goes up. So I don't know what the function U as a function of T looks like. I don't know its exact nature, but I do know that if you were to graph internal energy as a function of temperature, that I could shut my eyes and just say it's going to go up, all right? It's not going to go down. I know it's going to go up. I know internal energy is going to go up with temperature because I know the kinetic energy will go up. So let's suppose I start here, right? Let's suppose I start at temperature T1, okay? And my internal energy is U1. And let's say I put a certain amount of heat into this system. And I'm going to put this much heat. And I'm going to do it at constant volume. Okay, so put heat in at constant volume. Well, the amount that internal energy is going to go up is going to exactly equal the amount of heat that goes in, right? Because delta U is QV. So this is going to be my new internal energy. right? And this is going to be my final temperature, T2. So the temperature will have gone up this much. Okay? But now, what if I didn't put the heat into that substance, but I put it into something that has a higher heat capacity? And heat capacity tells you how much the temperature is going to change with a certain input of heat. And heat capacity is actually the slope of the U versus T curve. So something with a higher heat capacity is going to have a steeper slope. So let's say it's this, right? So this is for a substance with a greater heat capacity. And you could see that if you put the same amount of heat in, that the final temperature will be over here. And your change in temperature would be that. Okay, so for a substance with a greater heat capacity, the temperature goes up less with a given heat input. And in fact, the heat capacity is defined as the change in internal energy with respect to temperature at constant volume. So we call it the constant volume heat capacity. So the slope at every one of these points is whatever is the heat capacity of that substance. And like I said, I'm not pretending to know what this graph looks like, but I know it's going up with temperature. What's the matter, Karen? You're looking at me with that funny look. On.
Oh, sorry. For some reason, the screen with all the faces popped up, and I'm trying to get rid of it.
Oh, yeah. Yeah, good old Zoom. Yeah, I think I've mastered that by now. For some reason, I've figured it out. So does that make sense? You know, if you have something with a higher heat capacity, the internal energy goes up faster with temperature, but for a given input of heat, you actually get a smaller change in temperature. All right, so if we just work with this thing a little bit, we have CV is du dt at constant V. I can kind of write this as just saying in words, at constant volume, and then I've fixed the volume with my words, right? And I can just call this a plain old derivative. Okay, and then I can say, okay, that means that du is CV dt. Sorry, I have that wrong. Right, just so now I can integrate this, right? And I have two different situations here. So one situation is if CV is constant, if the heat capacity is constant, then I could take it out of the integral. By the way, is temperature an exact differential? Is the change in temperature path dependent? No, it's just delta T. So this is CV T2 minus T1. Change in temperature doesn't matter how you got to that temperature, it's just whatever. And this is the integral of du from state 1 to 2 is delta U, or U2 minus U1. Okay, so we have that delta U is CV delta T. And then I just want to say that a lot of times, you know, the CV that you use is a per mole quantity. So you would have to multiply this by the number of moles. You know, if it's not, if it's a per mole quantity. But the other thing that can happen is that CV is not constant with temperature. And this is especially important if you're integrating over a very wide range of temperatures. Okay, and then there's really, you have to know, well, how does CV depend on T? And you really couldn't simplify this. You just have delta U would be the integral of CV of T dt, and this is depends on T. It's not multiplication. Okay, so that's the other thing that can happen. And also, again, I'd have to put in a number of moles. Okay, so there are two different sort of recipes here for the change in internal energy when you heat up something. All right.
Dr. Cooley, what does it say? It depends on not what?
This means depends. Oops, sorry. This means depends on, not multiplication.
Okay. Thank
So
you.
that's that parentheses doesn't mean. I'll be right. All right. Okay, so we have this really nice relation between delta U and QV, the heat that flows at constant volume. These are equal, or du equals dQV in differential form. So unfortunately, in chemistry, we don't deal too much with constant volume processes. So what we're really interested in are constant pressure processes, because when you do a reaction on the benchtop or something like that, the pressure is constant. It's the atmospheric pressure. So what about constant pressure? Can we do something similar? So if we try to do that, so we start with our first law in differential form, okay? And I often leave out the slashes, but I'll try not to here. And then I say, okay, I know that there are two types of work. Hold on a sec. For constant pressure, because we really care a lot about constant pressure, because we care about benchtop reactions, mostly what, so we care mostly about constant pressure situations in chemistry. So we start with the first law. We break this down to expansion work and extra work. Then we say no extra work. Oh. Okay. It tells me I'm muted, but I'm not muted on my other thing. So, all right, so I can cross this out. Now I'll say, okay, dq plus, this is minus p external dv. All right, and now I specify constant pressure. And I look at this and can I simplify it at all? So there's only one little thing I can do, and it's really only a little thing. I can put a P here, right, specifying constant pressure, and then I could get rid of the slash because I've specified a path. Right, I specified constant pressure path. But I can't simplify this anymore. So I'm kind of stuck with this nasty looking thing at constant pressure. And there's really no simple relationship between delta U or du and the heat the heat that flows at constant pressure. So it's like a fail, right? Okay, so so that's why we invented enthalpy. This is why enthalpy came into being. So enthalpy is defined, H, as the internal energy plus the product of volume and pressure. And it looks completely arbitrary. Like, why would you define some new thermodynamic function that has this definition? But the reason why you define this way is because enthalpy becomes very simply related to the heat that flows at constant pressure. So if you start with this definition, and then you take the differential, and this happens all the time. Instead of taking a derivative, it's very similar, but we look at the change in each side. We take the differential of both sides. So H becomes DH, U becomes DU. Now what about PV? So taking a differential is really like taking a derivative. And so we have to use all the rules for derivatives. So when you differentiate a product, you have to use the product rule. And take the derivative of PV, you have to take the first times the derivative of the second, and the second times the derivative of the first. And you do the same thing here. So this becomes P dV plus V dP. Now, if you're not comfortable with that, I have a way of looking at it, but I'm not going to show it to you unless you really want me to. The way I try to understand this is, well, if you start with PV, right, and you change this, you change the pressure a little, and you change the volume a little, and if you multiply this together, okay, so you start with PV. You change P a little bit, you change V a little bit, but what happens to the product? So it becomes all this stuff multiplied together. Well, this is the initial. So we're going to subtract that out to find the change. And this is negligible. And if these were differentials, this would really be negligible because you're multiplying something that's really very close to zero by something else really close to zero. So basically, you end up with P delta V plus V delta P, and that's P dV plus V dP when you go to the infinitesimals. So when you take the differential of PV, you get P dV plus V dP. We'll do this over and over again. So make sure you get familiar with that. Okay, so I have this form, now I have DH is du plus P dV plus VDP. And now I'm going to use the first law. So du is dq plus dw. Right, notice already I'm not putting my slashes. I still have P dV and V dP. Okay, so now I'm going to use the definition of work? Well, first of all, I have to specify, well, can't do that yet. I have to make dq plus, I have to break this up to dw expansion and dw extra, but I still have pdv and vdp, okay? And now I'm going to say no extra work. I don't need any extra work. So this goes, okay? And now let me put in, by the way, there should be slashes here. I really should be obeying that rule at least for a little while. So now I put in the definition of expansion work. And I just did that. And now we have to look at this thing. Look at this, these two terms. They look very, very close, right? And one is negative and one is positive. So the question is, you know, can we cancel these? So if I say that the system and the surroundings are in mechanical equilibrium, so that the pressure of the system is equal to the external pressure, then I can cancel them. So that's what I'm going to say. The system and surroundings are in mechanical equilibrium. So that leads me to be able to cancel these out. And now I have one more thing to say. Constant pressure. So I have dH equals dQ plus VdP, and now I specify constant pressure. dP, the change in pressure, is 0 if it's constant pressure. I get to put a P here and take off the slash because I've specified a constant pressure path. You try to say that. Constant pressure path, constant pressure path. So we have dH equals dQP. And I love, like I said, integrating things like that because this just comes out to the heat that flows at constant pressure. And this is just delta H. So we have this really nice equation, which says that if you measure the heat that flows into or out of a system that's held at a constant pressure, you have just measured the change in enthalpy. Now, that doesn't really help very much if you don't understand what enthalpy is. So I will spend quite a bit of time talking about how you can, you know, how delta H and delta U are related to one another. Okay. First of all, I'd like to say that enthalpy is a state function also. And how do I know that? Well, I know it because it's defined as U plus PV. And U is a state function. Is pressure a state function? Is volume a state function? The pressure only depends on what the pressure is. It doesn't depend on what it was before and how it got there. And the same is true for the volume. So these are state functions as well. So enthalpy is also a state function. So that's how I was able to integrate dH to get delta H, because enthalpy is a state function. And H2 minus H1 or delta H is always the integral of dH. Okay. So knowing that delta H is the heat that flows at constant pressure, that explains why enthalpies of reaction that you see in tables, so you see standard enthalpies of reaction, for example, or a formation, whatever, they are often referred to as heats of reaction. So why would these be the same? And I'll use that a lot. I'll say, what is the heat of that reaction? I mean, what is the delta H? It's really the same. And that's because I'm assuming constant pressure. Because these are the same as long as pressure is constant. Okay. All right. So we have these great equations. We have du is dqv, dH is dqp, and the corresponding deltas. And so, I'd like to talk about how can we relate delta H and delta U? How are these things related? Because I think delta U, you have a pretty good understanding, at least of where that's coming from. It's the sum of all the different energies in the sample, but delta H, not so clear. But anyway, so I want to talk about how these things are related, and it starts with the first law, okay? So if you have this as the first law, and then, and you write this, we have expansion work and extra work, and then we say no extra work. So we have du is dq plus dw expansion. All right, so now, if the pressure is constant, so at constant pressure, this dq becomes dq at constant pressure. That's what this means here. But you can see clearly that dqp is dH. So we have this equation here. And it says that the change in, and you could, well, it says that the change in internal energy and the change in enthalpy differ by the amount of expansion work that's done. All right, so listen, let's suppose you have a reaction in solution. It doesn't generate any gas. It doesn't use any gas at all. Okay, no gas is generated. So there's no expansion work being done on the atmosphere. It doesn't get compressed. It's just these chemicals in solution. No expansion work. If that's the case, then delta U is the same as delta H. Okay, so there are lots and lots of cases where the change in enthalpy is exactly the same as the change in internal energy. And what does that depend on mostly? It mostly depends on the bonds that are breaking and the bonds that are forming. So both of these mostly depend on the bonds that are breaking and forming. And the bonds that are breaking and forming are not, I mean, it's this, so when you're that's the main thing that's happening, and that's what's providing these changes. And sometimes the difference, which is a little bit of work, is actually very small. So here, well, when there's no gas generated and no expansion work done, they're absolutely equal. And it's all about making and breaking bonds. But you can have some situations where maybe the moles of gas changes between the reactants and the products. Or maybe a gas is generated, or maybe something is heated up, like a gas is heated up and it undergoes an expansion, right? So situations where the moles of gas change. So some common cases where delta U does not equal delta H. They generally involve gases, so reactions that change the number of moles of gas from the reactant side to the product side. Okay, so if you have a change in the number of moles of gas, this usually leads to a kind of a small correction. In other words, delta U is not quite equal to delta H. So that usually leads to a small correction, a small difference between delta U and delta H. That class is over. I mean, it's 5:13 anyway, and I'm going to have to reboot this thing again. I don't get it.